Hello, this is Professor Martel, and this lecture is going to be about methods of proof, specifically methods of proof having to do with those Boolean connectives, right? Conjunction, disjunction, and negation. I want to go ahead and begin, though, with a few points of clarification concerning matters dealt with in previous lectures. So first up, a note on what I'm calling schemata, which is the plural of schema. So a bit needs to be said to clarify the use of uppercase letters from the English alphabet on the part of our textbook authors, Barwise and Etchemendy. P, capital Q, capital R, and capital S are used as sentence variables, much like the variables X, Y, and Z in algebra, for which numbers may be substituted. Sentences, or well-formed formulae, WOFs, may be substituted for these sentence variables. Okay? Thus, P wedge Q, capital P wedge capital Q, is a schema, which roughly means a pattern, from which complex sentences, in this case, the disjuncts of this disjunction, may be generated by substituting WOFs for variables. And as I note in parentheses here, the WOFs that you substitute for those variables, they can either be atomic, such as A is a cube, or complex, such as A is a cube and A is small. I didn't provide an example. Another one. Either both A is between B and C and A is a cube, or E is a dodecahedron, may be obtained in this way by substituting both A is between B and C and A is a cube for P, and E is a dodecahedron for Q, right? In that schema that I was just talking about, capital P wedge capital Q. So other expressions, such as capital A wedge capital B wedge capital C, are, when used by our authors, just sentences in which the capital letters are merely abbreviations for atomic WOFs. Okay, and so that might be an abbreviation for A is a cube, B is an octahedron, and C is a dodecahedron, for example. Okay. Now I need to make just a brief note about logical truths, the subject of the last lecture and slideshow. Recall that a logical truth is a truth that holds in all logically possible circumstances. A logical truth is also called a logically necessary truth, or even a logical necessity. So there's a connection between the notions of necessity and possibility. That which holds in all possible circumstances, that which is necessary holds in all possible circumstances, no matter what kind of necessity we're talking about. Now, there are different kinds of logical necessity, as you know. Recall that the tautologies are a subset of the logical truths. The tautologies, have to do with what is possible given the meanings of truth-functional connectives, right? Including the Boolean connectives. It so happens that the logical truths, tautological and otherwise, can be contrasted with physical necessity. A physical necessity is something that holds in all physically possible circumstances. Okay, so again, there's that connection between necessity and possibility. The physically possible is a matter of that which is consistent with physical laws, at least in part. That's one condition that they have to meet in order to be physically possible. Thus, nothing travels faster than the speed of light would be a physical necessity, if I have my physics right. So understood, that which is logically possible might not be physically possible. For instance, the ants in the the classic horror / sci-fi film Them are, rest assured, physically impossible, since not having lungs, they would immediately suffocate, right? As ants, they just have those, I think, they're basically like tubes, and the tubes don't have enough surface area relative to the mass of an animal that large to supply it with enough oxygen. However, it is logically possible that there are such ants, gigantic ants, size of buildings, since this is something that makes sense from a logical point of view. Relative to logical laws, this is something that can happen. It's possible. Similar considerations hold for superhero movies based on the Marvel comic universe, including Black Widow, although I have to say a better, more recent example might be like the last of the James Craig, sorry, not James Craig, Daniel Craig, James Bond movies. The guy is like within a few feet of massive explosions, right, regularly throughout the film, any one of which would have had enough concussive force to kill him, and yet he kept getting up and fighting anyway. It's logically possible. It's not physically possible, I'm sure. But this raises the question of what the logical truths are. A purported example of logical truth mentioned in passing by our authors is the law of excluded middle, the acronym for which is just LEM. This law can be expressed by way of the schema, capital P, wedge, tilde, capital P, right? P or not P. And any sentence derivable, right, from that scheme by substituting for P, right, is going to be something that is necessarily true. Relative to the system of logic we're studying, and that's the next point I make in the slideshow. Their claim that this is a logical law or a law of logic is true. That's a true claim, but that claim needs to be qualified. When they say that this is a law of logic, that's true, but it's true relative to the system of logic that we're studying. And that system is, of course, first-order logic. It is not true relative to what is called intuitionist logic. Intuitionist logic is a system of logic developed in connection with what is known as intuitionism in mathematics. Intuitionism in mathematics holds that mathematics is about that which can be proved by way of our methods of proof, rather than being about some independently existing mathematical reality that is just out there somehow, waiting to be discovered by mathematical researchers. Intuitionists are unwilling to accept a claim, call it P, simply because it has been proved that not P. Okay? No, they insist that P itself be proved before accepting P into the set of mathematical truths. And so, you may know that the state of Missouri is the show me state. I think that's actually on their license plates still. Okay. In other words, like this is a state where people they want you to prove it. The intuitionists are like that. Their view is it's not enough to prove that it is not the case that P, right, for us to then accept P. No, P has to be proved itself. It has to be proved too. Okay. This means that they do not accept the law of excluded middle, since by citing the law of excluded middle, we could infer P from tilde P. Okay. At this point, you might well wonder which system is right. The one that accepts LEM, right? So FOL, for example, or the intuitionist version that rejects it. Your professor's view is that neither is right. They're just different. And this means that the logical truths are relative to the system of logic with which one chooses to work. And so your professor finds himself in agreement with a bunch of ancient Greek philosophers who were called sophists, the most famous of whom, a fellow named Protagoras, most famously held that the human being is the measure of all things, of those that they are, and of those that are not, that they are not. Right? Logical truths, right? They function as a kind of measure, right? That we utilize when judging of the world, how it is. Okay. And what I'm saying is that those logical truths are actually relative to the system of logic that you choose to work with. That said, it's best to begin learning. If you have to learn about systems of logic, it's best to begin with FOL. Since once that has been mastered, intuitionist logic is relatively easy to understand. So on to the topic of this chapter 5, methods of proof, particularly methods of proof having to do with the Boolean connectives, conjunction, disjunction, negation. Okay. So, as our authors note, truth tables provide a method for establishing logical consequence in cases where it depends upon truth functional connectives. However, this method very quickly becomes unwieldy as the number of atomic sentences or sentence variables increases. Indeed, it quite literally becomes exponentially more difficult as the number increases, since the number of rows needed is 2 to the n, an exponent, where n equals the number of atomic sentences or sentence variables. Okay, and so this is one of the reasons why in versions of logic, symbolic logic that I teach, I spend relatively little time with truth tables. I think they're helpful for getting clear on the notion of logical consequence. I also think they're helpful as ways of getting clear on the meanings of those truth functional connectives, the Boolean connectives in particular. But they prove not very useful in establishing logical consequence, because it's very often the case, even when working with arguments that have been translated into FOL, it's very often the case that the number of sentence variables or the number of atomic sentences that we have to take into account is like, more than 5. and at that point, like the truth tables begin to become ridiculously large. The larger the table, the more time consuming it is to fill it out. And also the greater the possibility for error, right? Particularly if like a human being, right, is the one who's filling in, right, all the columns and all the rows, right, marking correctly T's and F's in every case. It only takes one mistake, right, somewhere, or one misreading, right, somewhere, right, to create errors elsewhere, leading to a false result. Fortunately, there's a better way, and that's proof, and this is why I tend to stress proof. Okay. So constructing a proof involves a stepwise procedure of generating new sentences from any that are given according to some set of rules. Okay. The rules are such that if they're followed, every sentence generated is going to be a valid inference from what precedes it. Okay, now, a valid inference, that's just another way of talking about a logical consequence of what, if anything, came before. Right? Let's call such a rule of valid inference a method of proof. Okay? You can think of the rule for generating valid inferences as a method, right? For generating new sentences, right? Based upon what, if anything, you're given, right? Leading up to a conclusion, leading up to and including a conclusion. There are several such methods, some of which you already know, and on the next slide I illustrate them. So we've got some methods of proof, formalized actually, like stated as rigorous rules, right? Connected with identity. So identity intro, right? That allows us to introduce at any point in a proof a wolf, identity symbol, that same wolf. Another method of proof we have, of course, is identity elimination, right? which itself depends upon that principle called the indiscernibility of identicals. We've also got De Morgan's laws, which allow us to infer from negations of disjunctions, conjunctions of negations, right? And negations of conjunctions, disjunctions of negations. Okay. And vice versa, right? Because De Morgan's laws have to do with schemata that are equivalent, that are logically equivalent, right? So if one of the pair, right, is true, then the other of the pair must be true. Okay. Other known methods of proof: commutativity, associativity, and idempotence. And I have to qualify my claim that these are known to you at this point, because they're actually covered in sections subsections 4.5 and 4.6 of Chapter 4. I did not assign those sections because we have relatively little time to work with. Here, in a quarter-based system, as this one is, instead of a semester-based system. Additionally, those sections have to do with negation normal form, conjunction normal form, and disjunction normal form. And those forms are really primarily of interest to people who are interested in computer science. Those of you who are interested in computer science may want to go back and take a look at them. They're relatively brief and straightforward, but given limited time to work with, I just couldn't assume that they would be of great interest to everyone taking the course. Additionally, it's going to turn out that we're going to introduce formal methods of proof, a limited number of them, that allow us to make do, that is, construct proofs perfectly well, without having to cite as rules commutativity, associativity, or even idempotence. But our authors did in fact mention these methods prior to chapter 5. Commutativity just has to do with the notion that the order of appearance of the disjuncts in disjunction makes no difference, right? P wedge Q, that's logically equivalent to Q wedge P, and that double arrow that you see on this slide, that's just the logical equivalence sign. Same thing holds for conjunctions, right? It doesn't matter which order the conjuncts appear in. As long as they're there, one is saying the same thing, right? They have exactly identical truth conditions. Associativity, that's the principle owing to which we in this system of FOL we don't require parentheses where you've just got disjunction, 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 for however many disjunctions there are. I should put it this way: when you've just got a series of woofs that are connected by wedge. We don't need parentheses in this case to disambiguate, because ambiguity in this case is not it's not harmful, right? Any way that we would disambiguate these sentences by adding parentheses would be equivalent to any other way of doing so. Okay, so to be hopefully more clear about this, either P or Q or R, that's logically equivalent to either P or either Q or R. Okay, and the very same thing holds for kind of a string of conjuncts, right? Yeah, there's ambiguity here, but it's not a harmful ambiguity because, no matter how you would disambiguate those expressions by adding parentheses, the result would be logically equivalent to any other way of disambiguating. Okay. Idempotence, that's just telling us that P wedge P, that's logically equivalent to P, and you could verify this really quickly using a truth table. Same holds for P conjunction P, that too is logically equivalent to P. Okay. So this chapter begins to introduce us to new methods of proof. Okay. One new method of proof is conjunction elimination, and that's a method that actually is going to be formalized, and you're going to have to use it when constructing proofs using Fitch. Okay, it's going to be in the menu. You've already seen it in that menu. The method tells us, the rule tells us, that given P and Q, P is a valid inference, as is Q. Okay, if you've already got in your proof a line that gives you a conjunction, right, of the form P and Q, a conjunction that fits that pattern, you can then go ahead and generate in your proof as a valid inference either of the conjuncts by itself. Okay. Another new method is conjunction introduction. Okay, so suppose you have a wolf on a line by itself somewhere in your proof, call it P. And at some point in the proof, there's another wolf, call it Q. Okay. If you have already in your proof, right, a line that says P, also a line that says Q, you can go ahead and infer, it's valid, P conjunction Q, okay, or P and Q. Another less obvious method, this is disjunction introduction. So this tells us that given P, you can infer P wedge Q, right? Yeah, this actually strikes many people as somehow wrong, like somehow like unfair, like somehow illegitimate, because it seems like in going from P to P wedge Q, you're adding information. Actually, our authors point out what you're really doing, if you think about it, is you're taking information away, because if someone only knew, right, P wedge Q and hadn't first been informed, right, also P, knowing just P wedge Q, they wouldn't know which of the disjuncts was true, right? I mean, they would only know that at least one of them is true, and incidentally, that's why you can infer, it's valid inference from P that P wedge Q is true. If you know that P is true, then P wedge Q must be true. The latter is a logical consequence of the former. Right? How is that so? Well, disjunctions are true just in case at least one of the disjuncts is true, and so P wedge Q has to be true given that P, right, is true. Okay. Anyway, it seems like there's some sort of illegitimate addition going on here. Additional information is being provided. No additional information is being provided. Actually, like in a way, like something less informative is being said. Just another note here. This is why our authors regard a very common name for this method of proof as deeply misleading. Like in other texts, actually very, very commonly used texts, this rule is called addition. When if you think about what I just said, the rule is telling you to do or that you can do really anything but that, right? No new information is being contributed here, right? Actually, like we're moving from something like more informative to something less informative. Okay, we'll get back to these methods. What our authors mainly want to do, though, in Chapter 5 is introduce you to two more difficult, much more challenging methods to understand. And they first want to present them like informally, just kind of like make you aware that you've already engaged in this kind of reasoning. And also to kind of get you familiar with engaging in this kind of reasoning sort of on your own, right? Then they're going to go ahead and give us a formal way of engaging in, formal ways, I should say, of engaging in these methods. So the first is called proof by cases, and the second is called proof by contradiction. So proof by cases, roughly it works this way, so informally. Given P wedge Q, and given that R is a valid inference from both the disjuncts, R is a valid inference. Okay, so if all you've got is either P or Q, right? And you know that, well, if P is the case, then R follows. And you know that if Q is the case, then R follows. Then you know that R follows from P wedge Q, right? You don't actually have to know which of the disjuncts is true, right? Or if both are true, you don't have to know that. All you need to know is, right, R follows. R is a valid inference from both. Okay. So when you go about constructing proofs in this way, whether formally or informally, what you want to do is, like note that P wedge Q has already been established, right? Either P or Q has already been established. And then you'll argue as follows. Well, assume the first disjunct, right? Then show that R is a valid inference from that. Then assume the second disjunct, right? And show that R is a valid inference from that. This allows you to then conclude that R follows from P wedge Q. Right? Note here that when you're just assuming each of the disjuncts in turn, you're not saying to your reader, oh well, P is true, right? Or oh, and then Q is true. No, all you're saying is basically suppose, right? We know P wedge Q is true. Suppose it's P that's true, right? Of these two. I'm not saying it is, but suppose it is, right? Well, then you can see, right, that R follows. Now suppose that Q is true. I'm not saying that Q is true, right? Because all we know is either P or Q. But suppose it is true. Well, then again, like R follows. Well, in that case, right, R follows from P wedge Q. It has to be true if P wedge Q is true. Proof by contradiction works in a similar manner. It's an essential move in this method of proof that you assume something. You just suppose something. You don't say it's true. You suppose it's true. In this case, though, you suppose it's true in order to prove that it is false. and you prove that it's false by showing that the assumption that it's true leads to a contradiction. Okay. Now what's a contradiction? Well, I mean, I say here in the slide, it has a special symbol. It's basically an upside down T. Okay. But like technically, what is it? Okay. A contradiction is the opposite of a logical truth. Logical truths are logical necessities, right? They're logically necessary truths. A contradiction is a logically necessary falsehood. Or, okay, it's a set of statements, right? That if you conjoined them, right? If you said and, okay, all of them, that would be itself a necessarily false statement. Okay? Our authors put it this way. It's either going to be like by itself, right, a necessarily false statement, or it's going to be a collection of statements, which as they put it, are truth table contradictory. And what this means is that if you set up like a truth table for them, there'd be no row in that table on which all of them take T, right? For every row, at least one of them takes F. And what that tells you is they can't all be true under the same conditions. Okay. Obvious, well, maybe it's not always, but another way of putting it, getting back to what I just said a moment ago, if you were to create a conjunction of all of those statements, right, clearly the conjunction would have to be false in every row. So it would be like necessarily, it would be necessarily false. It would have to be false in every row because the only way it could be true in any row is if, right, all of the conjuncts took T. But look, if those statements are truth table contradictory, then in every single row, at least one of the conjuncts would take F. Anyway, a brief way of explaining how this method works is that given that a contradiction is a valid inference from P, not P is a valid inference. Okay. So if having assumed P, we are able to show that a contradiction follows, right? We may validly infer, we may generate as a new line in the proof, not P. One more note before moving on to some examples. As you may have guessed at this point, we're going to formalize proof by cases by way of a rule that's going to be disjunction elimination. Okay. You may have guessed this because you may have noticed that a certain pattern is being followed when it comes to like formal rules for constructing proofs. And the pattern is that for every elim rule, right, there's an intro rule, right? So we've got identity elim and we've got identity intro. We've got conjunction elim and conjunction intro. We've got disjunction introduction, okay? Well, we're going to have like then disjunction elimination. That's going to be proof by cases. Proof by contradiction, you can actually see, if you look at the slide, that's going to be negation introduction. And so when it's formalized. And so we'll also have corresponding to that negation elimination. And you can probably already tell like how that rule is going to work. It has to do with some of those equivalence laws that were discussed earlier, right? I think at the same time that De Morgan's laws were discussed in the text. Anyway, we'll get back to that. So I have on the next slide an example of proof by cases. I sort of walked through the example informally, and then I have on the right of the slide a formal presentation of the proof in Fitch. Okay. You're not going to be asked to create such formal proofs this week. That'll be next week. So suppose that either A is a tetrahedron and small, or A is a cube and small. Now you don't know which, but you know at least one of those disjuncts is true, right? Okay. Let's suppose that the first disjunct is true, right? In that case, we're supposing that A is a tetrahedron and A is small. Well, then it follows that A is small, right? And it follows like trivially from conjunction elimination. If you know that the conjunction is true, then you know that each of the conjuncts is true. And so each of the conjuncts is a valid inference from the conjunction. Okay, well, let's suppose then next that the second disjunct is true. Now, if the second disjunct is true, the second disjunct is A is a cube and A is small. Well, then again, by the same method of proof, by conjunction elimination, it follows that A is small. So either way you go, you don't know which is the case. I mean, we don't know if A is a tetrahedron or if A is a cube, right? But either way you go, right, we know enough to conclude that A is small. That's a valid inference. Just note one more thing about that slide on which this example is given. If you look at the formal proof in Fitch, you'll notice that there are some indented lines in the proof. Okay, those indented lines mean that a supposition has been made. Okay, rather than an assertion, right? An assertion to the fact that like this claim must be true. There's just some supposing going on, okay? Assuming for the sake of argument, and this actually happens. You can see this where the pink parts are kind of divided by like a little sliver of white. This happens twice. Okay, first I assume the first disjunct, and then I assume the second, right? Inferring my conclusion, small a, in both cases. All right. Okay. Let me now go to proof by contradiction. And again, I've got an example, informal example on the left of the slide, and then a formal presentation in Fitch on the right. Suppose that A is a large cube that is to the left of B. So left AB, right? Suppose too that B is to the left of C, a large cube. It follows, despite the fact that we're talking about cubes here, right? It follows that A is not identical with C, right? There are two cubes, not one. And here's how I reason using this method of proof by contradiction. I begin just by assuming the opposite of what it is that I ultimately want to establish. Okay, I want to establish that something is not the case. Okay, so tilde p, in this case, right? P is going to be A is identical to C. I want to prove that's not the case. So I want to prove that A is not identical to C. I'm going to use proof by contradiction. I start out by assuming, not stating, but just assuming the opposite. So I'm going to assume that A is identical to C. Okay, so right, what else follows from that supposition together with what I already know? Well, we know that left of is a transitive relation. And so it would have to be the case, given what I've assumed, right, together with what we already know, given our premises, it would have to be the case that A is to the left of itself, right? A is to the left of B, and B is to the left of C, and A is identical with C, then A would have to be to the left of itself, right? But left of is an irreflexive relation, and so nothing is to the left of itself. This implies that A is not to the left of itself, okay? And so there's your contradiction right there, okay? A is to the left of itself. That's a necessarily false statement. All by itself, it cannot logically possibly be true, okay? The assumption that A is identical with A, that led by a series of valid inferences to that contradiction, okay? If our supposition leads by a series of valid inferences to a contradiction, the supposition itself cannot, it cannot be true, right? If we're making valid inferences and we end up with a contradiction, there is no way that what we started with can be true. Because after all, if it were true, right, and all of our inferences are valid, it would be impossible for anything that follows from it to be false. Some things that follow from it are contradictory, right? And so the supposition can't possibly be true. If it's not true, then its negation is true. As I noted, this method will be formalized as negation introduction, and I have a an example of a formal proof in Fitch using that rule over to the right. Again, you'll notice that there are some lines that are indented. That's because the first of the indented lines, A is identical with C. That's what I'm assuming, right? I'm assuming it because I want to prove the opposite, right? I'm going to prove the opposite by showing that that assumption leads to a contradiction, which actually I've done. Let me then go to the last of the slides. On contradictory premises. It's possible to construct a proof from contradictory premises. Recall that an argument is valid if it is impossible for all premises to be true and the conclusion false. In a case where the premises are contradictory, it is impossible for all the premises to be true. That's just a matter of definition. This means that any wolf is a valid inference from such premises. After all, if the premises are contradictory, it can never be the case that the premises are all true and the conclusion false. And so it doesn't matter what your conclusion is. It can be anything as long as it's well formed. You're going to be left with a valid argument. Okay. To illustrate this point, I've constructed a proof of D is not identical with D, starting from the premises of the final exam problem. Those premises are contradictory, owing to the meaning of right of. Any wolf is a valid inference from such premises, including contradiction. Okay, so I mentioned this partially for two reasons. Actually, I should say three. One reason is that our authors do cover this possibility at the very end of Chapter 5. Another reason, though, is I think it helps drive home the point that there's a difference between validity and soundness. Sound arguments have to have all true premises. And of course, given that they're valid, they're going to have a true conclusion as well. So clearly then a sound argument cannot have contradictory premises. But a valid argument can have contradictory premises. Okay, validity. it is not something that you can establish then by just looking at whether the premises are true or false, looking at whether the conclusion is true or false, looking at the premises and the conclusion and seeing whether they're true or false. A valid argument can have one false premise. It can have two false premises. It could have all false premises. It can even have all false premises and a false conclusion. That's the case in the example that I just provided. It can even have a necessarily false conclusion and necessarily false premises, right? Either one of the premises can be necessarily false, or the conjunction of those premises would result in like a necessarily false statement. All those things are possible for a valid argument. Okay? You can't just look at the actual truth values that the statements in the argument are taking and go, oh, you know, there are falsehoods here, or there's necessary falsehood here, and so it's an invalid argument. No, right? Validity has to do with the relationship between the premises and the conclusion. Okay. Specifically, it's impossible for all the premises to be true and the conclusion false. Whatever's going on actually, that's something that cannot possibly happen. Okay. All right. I'm going to go ahead and conclude it here. As usual, look for some homework review, possibly some exam review later this week.